Hello students, welcome. This is Dr. Mayadurni again. This is chapter 4, periodic tables and its elements. I hope you remember we discussed 4 quantum numbers in chapter 3, which is principal quantum number, which is n, describe the energy of an each orbital. What is next? Angular momentum quantum number, which is L, describe the shape, and then you can find, depending on the L, you can find L is 0, it is S orbital, L is 1, it is P orbital, L is 2, it is D orbital, and so on. So then we talk about magnetic quantum number ML. It talk about orientation of orbitals in space. So S orbital, it is just one spherical S orbital, P orbital. It is -1, 0, +1. So it's 3p orbitals. D orbital, it is 5d orbitals. -2 to +2. So like that we discussed. So I told you why we are talking about these quantum numbers. The main reason we are talking about the quantum numbers to talk about electron configuration. To learn about the electron configuration. What is electron configuration? Electron configuration is how electrons are distributed in various atomic orbitals. How this atomic orbital means, remember I told you, okay, this is a nucleus, you go away from the nucleus, principal shell 1, principal shell 2, and so on. So, think about hydrogen atom. Hydrogen atom has one electron. How this one electron located in the um, the one electron in the atom. So here I'm showing you. So this so if you think about the nucleus, talking about hydrogen atom, this is my nucleus. N equals 1, N equals 2, like that. So the one electron, it should be closest, right? The one electron of hydrogen should be the closest cell, the closest atomic orbital, which is N equals 1. What is L? If n equals 1, L is 0 to n minus 1. So L is 0, which is s orbital. So that means the closest electron that is to hydrogen, it's situated in one electron. So it's in 1s orbital. So how do you show it in the orbital diagram? So you're drawing each orbital like a 1 square. So you draw half arrow up, that is 1s orbital. And then think about helium. Helium has 2 electrons. They are always to sit closer to the nucleus. Helium has 2 electrons, so 1 electron, and then they go down like that, 2 electrons. And if I go to the next one, next slide. I'm sorry, if I go to the next slide, think about so hydrogen. But if the hydrogen electron happen to in the 2s state, that means it takes energy and goes to the higher energy states. So hydrogen electron can go up to higher energy states, and then when it releases energy, if it is come to the Mama series, which is final state in 2, it can see it in colors. So in multi-electron atom, we already discussed this a little bit because, hydrogen, electrons, so very first, this is the closest to the nucleus, 1s. And then 2 electron fills, it goes into the 2 second shell. So then here, let me draw it. 1, so it's n equals 1, like that. So n equals 1, L equals 0. N equals 2, L equals, so it's 0 to n minus 1. So 0, 1. What that mean? L is 0 and 1. 0 means it's s orbital. L is 1 is its p orbital. So it's s, you have only 1 orbital. But p you have 3. You draw it like 1, 2, 3, like that. So n equals 3 level you go, L can be 0, 1 and 2 because L equals 0 to n minus 1, 0 to 2. So it's 1, it's you have 3 p's, 1, 2, 3. This is 5, 1, 2, 3, like that. So the electrons can be like up and down. It goes like that. So that's what it's showing in these diagrams. And then you go to the, yes, go to the next one. So always it's so this is the way you write the electron configuration. You write one as an example for hydrogen. I told you it's one electron and it's in the closest shell. Sorry, got it. Okay, so it's in the closest shell. So it is. You write it in. So it's one electron. So you write 1 is 1. So 1 is 1. 1 is the principal quantum number n. S gives the angular momentum quantum number, which is 0. And 1 is the magnetic quantum number. Electron spin can be plus half or minus half. Since this is 1, you write always it's plus half. But if you have 2, this is plus half. This is minus half. So, now, before I come into the Pauli's exclusion principle, let's take helium. Helium, 2 electrons, right? You write, because it's a closest shell, so it's in 1s, up and down. So how do you separate these 2 electrons? This n for these both, principal quantum number 1. L is 0. Ml is 0. Spin, each electron is unique, so there should be a definition. So because of the spin quantum number, this electron is plus half, this electron is negative half. So because of the Pauli's exclusion principle, they always we say, according to the Pauli's exclusion principle, no electrons in an atom can have the same 4 quantum numbers. So that's what it says. So because of the Pauli's exclusion principle, we see each electron in the helium atom has 2 different set of quantum numbers. That's only because all 3 same, principal quantum number is same, angular momentum, magnetic same, but spin is different. So that is the Pauli's exclusion principle. In the exam, I may ask, what is Pauli's exclusion principle? Aufbau principle. Aufbau principle is another thing you need to know when you write electron configuration. The Aufbau principle states that electrons are added to the lowest energy orbital first before moving to the higher. So it always first one is fill and then go to the second level. That's Aufbau principle. So it's always one is fill and then go to the second one. So it's in the total of 5. First you fill 1s, 2s, and then go to 2p. And this is another rule. The other rule is Huns Rule or Huns Rule. This is important. So think about, let me take from the beginning now. And coming to the Huns Rule, let me show you the electron configuration of atoms. So hydrogen, like this color, hydrogen, I can write it. Okay, it's okay. So let me, I don't know, I can write it. Hi students, I don't think I can show you the writing part today. The writing laptop is not working. But let me explain you the Huns Rule. Huns Rule is, according to the Huns Rule, so in the carbon, you have 6 electrons. So one is filled, it goes 2 electrons. Then you have 4 more to fill, right? So then go to the 2s. And then you filled 4 electrons and you have 2 more electrons. So the next 2 more electrons go to the p shell. When you go to the p shell, it is how many p orbitals? 3p. There are two possible ways it can fill. It can fill, the both electron can fill here in one orbital, or they can fill singly, right? So the rule says, so there should be a unique way of filling it, because otherwise I will draw one way, you will draw another way. So always Huns rule states that the most stable arrangement of electron is the one in which the number of electrons with the same spin maximize. Other words, when electron filling in the degenerate orbitals, the new word, degenerate. What is degenerate? Degenerates are the orbitals with same energy. These three orbitals have the same energy because it's the same level. First it fill singly, then it pairing up. So that is the Huns rule. So those are the main rules that we need to know in filling the electrons. So here I have nitrogen. 1s2, because nitrogen, first you check before writing electron configuration, the very first thing you see, okay, how many electrons in nitrogen? Nitrogen has 7 electrons. So it first 1s2. You have 5 more, goes to the 2s2. There is no so 2s2, and then you have 4 electron fill, 3 more go to the 2p3. One another thing, there is a cap of number of electron filling to the each orbital. 1s, always s orbital filled up with 2 electron. Why? Because in s you have only one little square. One little square can accommodate only 2 electrons. 2s also same. And then when you go to 2p, how many electrons you can see? Because each square accommodates 2 electrons, we have 3 of it. P goes to 6 electrons. So up to 6. So now I have another question. What about D shell? D shell you have -2 to +2. So how many? -2. I'm counting. -2, -1, 0, 1, 2, 5. 5 little squares. Each square take 2. So it's 10 electrons in 5D level. So when you have the oxygen, which is total of 8 electrons, first it fell, okay, 1s2, 2s2. So all three fill, it's 7. Now you have one more, that 8 comes here. Okay. So then they have neon, the 10 electrons. And then, so this is how the general rules of writing electron configuration. First one, electrons will reside in the available orbital lowest possible energy. So the lowest, so it goes from 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. You may wonder why there's no D, because think about the L. L for n equals to 0, 1. 0 means s orbital, 1 is p orbital. So for the first principal shell, only s. For the second principal shell, you have s and p. When you compare to the third one, s, p, and d. Each orbital can accommodate a maximum of 2 electrons. We already learned that each this tiny little orbital. Electron will not pair in degenerate orbital if an empty orbital is available. That is Huns rule. When it filling in the p orbital, first fill singly, then pairing up. Orbitals will fill in the order indicated in the figure. This is a good one to remember. Think about writing it. 1s, 2s, 2p, so it's always like that. So it goes fill like that, and then it goes like that, and then that it goes always. So there's a worked example. Write write the electron configuration and give orbital diagram of calcium, which is Z equals 20. So you have to fill these 20 electrons. So you look at that pattern. You write 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, like that, and then up to, then you start filling it. So 1s2, 2s2, 2p6, 10 electrons gone. How do I know? 2, 2, 4, 6, 10, 3s2, 3p6, and 4s2. So it's until you fill the 20 electrons, you write that. So then I'm coming to the electron configuration and the periodic table always you can get a lot of information about the position of an element in the periodic table from the electron configuration. Very first thing, if it is electron configuration ends with s orbital, that means element is in the s block. And also think about this one, the ground state configuration of potassium. So there's another way of writing electron configuration. You use previous closest electron configuration, like previous closest noble gas. So if you see 1s2, 2s2, 10, 18, right? 18 goes to, if you see here, this is argon. Argon is 18. So instead of writing all these numbers, you just write argon and the brackets, and then you write 4s1. That is another way of writing. And also, so then the transition metals, whenever there's a transition metal, there's a blocks in the periodic table. This we call S block. If you write electron configuration of any of these species, it ends with S. This we call P block, right electron configuration, ends with P. If I make it a little bigger for you so I can show you. See, these are ends with S. These are ends with P, so we call this as P block. All these ends with P, so we call them P block. The square goes bigger because I just make it bigger. So it's all, this is D block. This ends with F, so we'll call F block. I'm not going to go with too much with the F block electron configuration, but S, P, D, S. So this is the lanthanides, actinides. So here are the blocks. This is S block, D block, and P block. So if I say electron, so there are several notable exceptions. So example, chromium, there are some exceptions. So chromium, always you write, so argon 3s2, 4d4, but the reality, always the 3D has, so this is the chromium. Chromium has 5 orbitals, right? So if you write S2 and D4, this orbital is not filled, not even half filled. D is a very big orbital. So they like to be at least half filled. So in order to be half filled, this D take 1 from S, and so it's at least half filled. So the half filled orbital has a greater stability. So because of that, and actually you can, the correct way of writing chromium electron configuration is argon 4s1, 3d5. Same with copper. Copper, if you write, it's 29. You write copper, argon 4s2, 3d9, but 9 is not filled. Not always. Why the noble gas is stable? Because they have fully filled shells. So these orbitals try to fill, like at least half fill. That's happened with the chromium. When it comes to copper is 3d9, you need only one more electron. You may wonder why it asks from, why then when it asks electron from S, it's not, but S is very small. D is very big. By filling D, it gains higher stability to the element other than 4s. It's a little orbital, tiny orbital. So I have a question. Write the electron configuration for an arsenic atom in the ground state, which is 33. So arsenic, so you look at where's arsenic. So you go, it's easy way. So it's Z is 33. You look at where's arsenic in the periodic table. You get to use a periodic table is here, arsenic is here. So you look at closest previous noble gas, which is argon. Argon, it's gone 18. So, but you have 33 now. So you write argon within brackets, argon, and then you start, okay, how do I know this is 4? Is because it's period 4, period 1, period 2, period 3, period 2. I know this is S. How come? Because it's S block. 4s2, 3d10, 4p3. Argon 4s2, 3d10, 4p3. That is how I write argon. You can write the longer way. 1s2, 2s2, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. It doesn't matter, but that's easier. If you look at the periodic table, closest previous noble gas, and then write the electron configuration. That is a one way of writing the electron configuration. So I hope you have a good idea of how to write this electron configuration now. And I have a separate video, just not the PowerPoint, how to write electron configuration. Please watch that as well. And hope this helped you, and thank you so much.